Moving on to topic E, and this is again November 21. Uh, and PHOSL. Those of you who are SL, just understand which is not part of the SL content and skip over those. The detector measures the count rate from a sample of radioactive nuclide. Graph shows variation with time of count rate. Nuclide has half-life of 20 seconds. The average background count rate is constant. What is the average background count rate? Okay, so we have half-life of 20 seconds. And so the count rate, let's look at this. 19 minus x. Let's let this be the background count rate. And so after 20 seconds, what we have is 11. So let's just look at that. So half of 19 minus x is equal to 11 minus x again. And so what we have is 19 minus x is equal to 22 minus 2x. 2x comes here, x is equal to 3. And so that's our background count rate, and our answer is C. Okay, now what's up? Now, 21. The mass of a nucleus of iron 56 is M. What is the mass defect of the nucleus of iron 56? So mass defect is just our sum of nucleon mass, right? Minus the actual mass, actual nucleus mass. And so what we have is 56 minus 26 at 30 neutrons plus 26 protons, MP, minus Rm. And so which one is that? That is B. Oops. That is B, so our answer is B. Now the reason, so our nucleus, the mass of our nucleon should always be, let's write this, individual nucleon mass always greater than uh the weighed nucleus, combined nucleus. Because there is that mass defect, right? That binding energy. So difference is equal to M, which is equal to, or creates our binding energy, right? Which comes from our E is equal to mc squared. So let's move on to 20. This is topic B. Let's move on to topic E. We have one here. The photoelectric experiment at a stopping voltage V. This graph required to prevent photoelectrons from flowing across the photoelectric cell, measured for 2 frequencies. Okay, the results are obtained. And so I drew this line so we can see our gradient. Let me just do this. And so the ratio is an estimate. Let's see. So this is gradient, right? V2 minus V1 over F2 minus F1 is equal to our gradient. And what is our gradient? Let's see. So we should remember this for stopping voltage, or work done, is our Emax, right? And our Emacs from topic D, which is our work done from topic D, is charge times stopping voltage when we have an electron or any charge, but that is also equal to our HF minus work function, right, from topic E. And this comes from, and this comes, let me actually just write this down. This comes from our KE max, right? And that is energy required stop even the fastest electrons. Let's say photoelectrons, right? Because we're talking about the photoelectric effect. Photoelectrons. And this is our stopping potential. Stopping potential. And so that is equal to our photoelectric equation, right? And so we can solve that now. Let's see. And what is the charge of an electron? E. We're talking about an electron, right? Yep. Photoelectric effect. And so what we have is H E F minus work function over E. So what we have here is our gradient, and that is what we're trying to find. So H E, and so our answer is E. And we can see our y-intercept would just be that. Somewhere here, right? Negative. So, yeah, that is our answer for 37. Let's move on to 39. Some of the nuclear energy levels of oxygen, nitrogen 14 are shown. Nucleus of 14 decays into nucleus of nitrogen 14, which with the emission of a positron and a gamma ray. What is the maximum energy of the positron and the energy of the gamma ray? Okay, and so our positron is emitted when we have this, what is it? It's an emission, right? So when we have this positron, which is beta plus, is emitted, and we have a neutrino. And let's actually put the charge here, +1, 0. And we have our neutrino. And so this is what carries our energy, right? The energy difference. And so what we have is 4.1 minus 2.3 is equal to 1.8. And so that's split between these two. And our maximum energy of positron is when that is 0, right? Approaching 0. So it would be close to 1.8. So it's either A or B. And then we have our energy of a gamma ray. Now, our gamma ray is a photon, right? It's a photon that is usually emitted when this uh, atom transitions to a lower energy state from an excited state, and that's usually at the ground state, and that's why they've given that to us. And so when it comes back to the ground state, it emits its gamma ray, which is just a photon that has an energy equal to this energy difference, right? And so E is equal to 2.3 minus 0, which is 2.3. And so the energy of a gamma ray maximum would be 2.3. So our answer is A. Let me circle that. And last one, question 40. The size of a nucleus can be estimated from an from electron diffraction experiments. What is the order of magnitude of the de Broglie wavelength of the electrons in these experiments? And so this is actually quite difficult, right? What we're told is the size of a nucleus can be estimated. So we can only estimate the size of something. We can only resolve an image or size with a wavelength that is of same order of magnitude or comparable, same order of magnitude or comparable, similar, right? And so as the object it's can only see or resolve, let's say, right? Waves size only with a wavelength of same order of magnitude as the object. And so we can only estimate the size of a nucleus if the de Broglie wavelength, the wavelength of the electrons, is approximately equal to the radius of this nucleus. And so we can use our equation for Fermi radius, and that is approximately, check, I believe it's 10 to the negative 5 to 1.2, yes. 1.2 times 10 to the negative 15 meters, which is around the order of magnitude of the radius of the nucleus. And so what we can say is our answer is A, and that's something we just have to remember. So, and same thing goes for anything, sound or radio waves. The object it's measuring has to have the same order of magnitude as the wavelength, similar size. And that's why our slit diffraction sort of experiments need to have extremely small slits to match the wavelength. And that's it for topic E. Hope you guys learned something and this was helpful. Please drop a like and subscribe.